You'll notice I have an extension cord running to my circular saw. This works as a series circuit. The extension cord acts as one resistance. The saw acts as a second resistance. In this example, I would want the resistance of the extension cord to be as small as possible and the resistance of the saw to be significantly larger than the extension cord. The reason is I'm going to be using 120 volts, which means I have to lose 120 joules during this process. And I'd like the majority of that lost energy to turn into kinetic energy in my saw. I do not want energy turned into heat within my extension cord. So again, the combined resistance for these two would be my total resistance because they're in series. I want the resistance here to be significantly larger than it is in the extension cord because I'd like most of my energy lost in the saw and less of my energy lost in the cord. I would like to show you a dimmer switch in action. So you'll notice behind the cat there is a dimmer switch, and up here is the light bulb that it controls. And these two are connected in series. And if I adjust the dimmer switch, you'll notice that the light bulb gets less and less bright. No matter where I put the switch, the total voltage for the system is 120 volts, which is 120 joules per coulomb. But by having a larger percentage of the resistance here means that we have less total current flowing through our light, which means less of the energy is lost in the light and more of the energy is lost in the switch. Working on these series circuit problems. On the first problem, we're going to be dealing with that dimmer switch that I just showed you. These two pictures represent the exact same circuit. The light bulb in the series with the variable resistor. So you got the light bulb and you got a variable resistor. On the left, the variable resistor is set to 0 to make the light as bright as possible. So when you're dealing with this problem, the one on the left, you could ignore that variable resistor altogether and just do a real simple Ohm's law problem. Find out how much current's flowing through the circuit. Find out how much wattage the light bulb will receive. Then on the right, we set the variable resistor to a value that will dim the light. So I'd like you to, in this one, treat it like a series circuit. Find your total resistance, your total current, find the voltage for each component, and then find the power for each component. When you're done this problem, put the answers in this picture. So I already have the units, just click in those boxes and put the answers there. And then I want a neat picture of your work on the next slide. Make sure when you put your picture here that you get rid of this text box. Make sure your work is neat and legible and that I can read it easily. Okay, the next problem we're going to deal with is the wire in my toaster. So the wire in the toaster has a resistance of 18 ohms. The toaster is hooked to a standard 120 volt outlet. I'd like you to find the current that flows through the toaster and the power of the toaster. So treat this as a simple one element circuit using Ohm's law and the power equation. You can put your work for this problem, because it shouldn't be much, as a picture right below this chart. Make sure all your answers go into that chart. Now the same toaster is hooked to an extension cord that has a resistance of 1 ohm. This is also a series circuit. So you have the wire inside the toaster in series with the extension cord. So this time treat it like a series circuit with two resistors. One resistor is the extension cord and one of the resistors is the toaster itself. Find the current that flows through the circuit, find the voltage for each part, and find the power for each object. So I have a chart here to help you organize your thoughts. I give you the two resistances. Get the total resistance. Use the total resistance to get the total current. In a series circuit, all parts should get the same current. Use those currents to find the voltage for the toaster and the voltage for the cord, and then find the power for both and the total power. Realize that any power generated in the cord is wasted energy. It's energy that's going to heat up that cord. So we want this resistance to be as low as possible, and we want the toaster resistance to be significantly higher, so that most of the voltage is lost in the toaster. Okay, for your work for this one, again, make sure it's nice and neat, and put that work on this slide. And again, get rid of the text box. Make sure your work is legible and neat, and large enough for me to read. Hopefully, like I said, you see that the wire in the toaster needs to have a higher resistance than the wire that brings the electricity to the toaster. If the extension cord's resistance is too high, it too will get hot and could start a fire. So when I was telling you guys before that we want higher resistance wires, realize that's a relative statement. The wires that are generating heat should be a much higher resistance than the wires carrying current to the device. But if the wires generating heat have too much resistance, you won't get a lot of current going to them, and they will never get hot. So it's got to be a good balance. The resistance of the toaster wire should be high in comparison to the cord bringing the electricity to the toaster. But it shouldn't be so high that we don't get a lot of current.